inviting me here to come to Daegu and give 2 lectures at this workshop. It's always a great pleasure for me to come here. I also would like to thank the organizers for putting so much effort into organizing everything here. It's very well organized. So the topic of my talk is hypersurfaces in symmetric spaces. The basic idea for what I want to talk about, the basic problem, is very simple. It's about the problem of finding submanifolds in a given space which have the same shape everywhere. Yeah, so submanifolds which just look the same at each point. I mean, for example, you see, when you are in a 3-dimensional space, what surfaces come into your mind which have the same shape at every point? Well, certainly a plane. Yeah, so you see, when you draw a plane, and no matter at which point you are, your intuition tells you it just looks the same at every point. Yeah? And probably it's not difficult to think about another surface in the 3 space, which is the sphere. Yeah? And it doesn't matter on which point on the sphere you stand, it just looks the same at every point in each direction. Yeah? Another example is the cylinder. Yeah, also here, when you are on an arbitrary point on the cylinder, yeah, it just looks, and look in each direction, just looks the same everywhere. Yeah? So you don't really need mathematics for this, it's just your intuition. But what you need then mathematics or geometry for is to show that in a 3-dimensional Euclidean space there are no other surfaces with this property. Yeah, that's intuitively not so clear, and you need to do some work for this. Yeah, this was, I think, for the first time, this was proven by an Italian theoretical physicist about 100 years ago, by Somigliana. And then there are many different proofs now for this fact. And what I want to talk about is some generalization of these questions to other spaces. Yeah. And one of the generalizations, this is a classical theorem now by Elie-Cartan. It deals with this problem in real hyperbolic space. So when you think about what do I actually mean when I say a surface has the same shape at every point. So the shape is measured somehow by, when you look at normal vectors, how they move along the submanifold, along the surface in directions. Yeah, and then how that measures somehow how the submanifold is curved. Yeah, so the mathematical object measuring this is the second fundamental form, or the shape operator. But this is basically characterized, this is a symmetric tensor field, and symmetric tensor fields or symmetric endomorphisms, they're uniquely characterized by their eigenvalues. These are the principal curvatures. So when we put on the condition of same shape at every point, this is the same as saying we have the same principal curvatures at each point. Yeah, so this is the mathematical quantity we want to consider. Yeah, so same shape at every point means same principal curvatures at each point. And then Elie-Cartan proved that when we are in a real hyperbolic space and we have a hypersurface, so in this talk I want to concentrate on codimension 1 submanifolds, hypersurfaces, although one can ask these questions also for higher codimensions. It just becomes a little more complicated technically. Yeah, so I'm going to talk about hypersurfaces. So a hypersurface in real hyperbolic space has constant principal curvatures precisely if it is an open part of one of these hypersurfaces. So there are not so many. The first one is a horosphere in real hyperbolic space, and I need to explain what a horosphere is. It has nothing to do with horror. A horosphere. So consider a geodesic ray in a space, here in the real hyperbolic space, or maybe for the moment just in the Euclidean plane, because this board is like a Euclidean plane. So consider a line segment, yeah, which is a geodesic, starting at one point, say at the point P, and then going to infinity. Okay? So now what we do is we consider a family of spheres. So a family of spheres which all pass through this point, and for which the center of the sphere lies on this line. Yeah, and then the center moves to infinity. So we consider spheres. Here is one sphere, small sphere. The center is on this line. Then we take a bigger sphere, or a bigger circle in this case when we are in dimension 2. The center is on this line. Yeah, and we continue with this process. Okay, so we get larger and larger circles all passing through this point. Yeah, and now imagine, use your imagination, you continue with this process, you get larger and larger circles, and what do you get in the limit? In the limit, you get precisely this line yeah, the line which is perpendicular to this line. Yeah? And this is what is how a horosphere is defined. It is the limit set of a family of geodesic spheres, all passing through one point, and for which the center of the spheres tends towards infinity. Now that's the definition of a horosphere, and on certain spaces, so on spaces which have negative curvature and are simply connected, like Euclidean space or real hyperbolic space, what we get is always an analytic hypersurface through this construction. It's not obvious that it's an analytic hypersurface, but one gets it. Yeah? So that's a horosphere. And a horosphere, so one can do this construction in real hyperbolic space, and the horosphere has constant principal curvatures. Maybe it's not so surprising, because spheres in a real hyperbolic space have constant principal curvatures, so you somehow would expect that when you go to a limit, that this condition is preserved. Yeah, so what one also gets is a totally geodesic. A real hyperbolic plane is, of course, has constant principal curvatures. All the principal curvatures are zero, or equidistant hypersurfaces, so the hypersurfaces which have a fixed distance to a real hyperbolic hyperplane, or tubes around a higher dimensional real hyperbolic space in k-dimensional real hyperbolic space. So there are only very few of them. So maybe one striking result is, of course, this is a complete classification which is quite satisfactory, but there is something quite interesting in this theorem, because all these hypersurfaces which are listed here are homogeneous, which means they arise as an orbit of a subgroup of the isometry group of real hyperbolic space. Yeah? And this is quite remarkable, because we start off with a condition of constancy of principal curvatures. Yeah? So we have these functions, these principal curvature functions. We just require that they are constant, and as a consequence we get a condition on the isometry group of the hypersurface. Yeah? It's a large isometry group, so in fact what we get is a homogeneous hypersurface, and that's quite remarkable in this result. It's not obvious at all. Now I want to also say a few words about how did Cartan prove this, because this gives some good insight into the general problems of this kind. So if we denote by G the number of distinct principal curvatures of the hypersurface, then Cartan proved that there are at most two distinct principal curvatures. And he used this by somehow mixing the Gauss and Kodazzi equations. Yeah, so you put in the condition that your principal curvatures are constant. You differentiate. When you differentiate constant functions, you get 0. You use the Gauss and Kodazzi equations. You get some equations out of this. And if you do this in the right way, you get as a conclusion that there are at most two distinct principal curvatures. Yeah? So there can't be 3, 4, 5, or I don't know, infinitely many. It's just at most 2, which is quite remarkable. Now when there is just one principal curvature, we have an umbilic hypersurface, and it's easy to classify them. One can just get spheres, or a hyperplane, or a horosphere, or the hypersurfaces which are parallel to a hyperplane, to a hyperbolic hyperplane. Yeah, so this is quite a straightforward thing to do. When one has two distinct principal curvatures, the basic idea is, so you start with the hypersurface and then you look at parallel hypersurfaces. And what happens when you have two distinct principal curvatures, there must be a focal set. So the normal geodesics emanating from the hypersurface, they must come together at some point. Yeah? So what you get is a focal set, and this gives you some additional information about the structure of the hypersurface. Namely, the hypersurface is geometrically a tube around a lower dimensional submanifold. And then one can use, again, the Gauss and Kodazzi equations to prove that this focal set must be totally geodesic. So as a conclusion, one gets that the hypersurface must be a tube around the totally geodesic submanifold. So eventually what one needs then is the classification of totally geodesic submanifolds in hyperbolic space. And this is quite a simple thing to do. One gets just real hyperbolic subspaces. Yeah, and this, when one puts this all together, one gets the classification. And so this is somehow the general idea of proving this result. I mean, there are other ways to do it, but this is the way Cartan did it. Okay. So here is a comment, is an observation, that real hyperbolic spaces and also spheres of dimensions different from the dimensions 19 and 31 are the only known symmetric spaces for which a classification of hypersurfaces with constant principal curvatures are known. Now when I say symmetric spaces and you don't know what is symmetric spaces, write down a few examples. For example, a sphere is a symmetric space, or we have projective spaces, complex projective space, quaternionic projective space, a Cayley projective plane. We also have Grassmannian manifolds, a Grassmannian manifold of k-dimensional subspaces in Rn. This is a symmetric space. Maybe we want the oriented one to have simply connected, or Grassmann manifolds of k-dimensional complex subspaces in a complex vector space. So there are many of these manifolds. Yeah. Or one has dual spaces. These are all compact spaces. So non-compact spaces, there is a one-to-one correspondence between these spaces, these compact spaces, and some non-compact ones. You have a real hyperbolic space, complex hyperbolic space, quaternionic hyperbolic space, Cayley hyperbolic plane, and then here we have, well, these are so-called Lagrangian Grassmannians, or so how should I say, GK, something like this maybe. Yeah. So these are examples of symmetric spaces. Among all these spaces, one can classify them. Elie Cartan did this. It's quite a nice list of spaces. There is only the real hyperbolic space and the spheres of dimensions different from these are known, where one has a complete classification of these hypersurfaces with constant principal curvatures. Yeah? So it's actually quite still is an open problem, yeah, to classify them in many other spaces. This is, I'll say more about these two dimensions in a minute, why these arise here. Yeah, so not much is known really. But what I want to do in these talks is to say what is known, how one can prove these results, and what the problem is, why one actually can't solve the problem. Yeah? And so in my talks I will present you with a number of open problems in this context. So the notation I want to use is M will denote a Riemannian symmetric space. So it's maybe, if you like, it's one of these spaces over there on the board. And for simplicity, I will always assume that our manifold is simply connected. But we don't have, I mean, in general, one doesn't have to put this condition, but it's easier to do this here. We assume that P, the hypersurface, I denote this one by P, and by G, the number of distinct principal curvatures. So, and I want to talk about spheres first. Spheres, this is actually a very classical problem, classifying hypersurfaces with constant principal curvatures in spheres, and this is equivalent to classifying isoparametric hypersurfaces in spheres, though I don't want to say much about this with the isoparametric. So let's assume that we have a hypersurface with constant principal curvatures. So we saw that Cartan proved that in real hyperbolic space we can have at most two distinct principal curvatures for a hypersurface. And such a constraint on the number of principal curvatures also exists in the sphere. But there this number can be 1, 2, 3, 4 or 6. Yeah, this is quite remarkable that there are these 5 different numbers which can arise as as the number of distinct principal curvatures of a hypersurface in a sphere. This was proved by Münzner, and the methodology for proving this is actually topology, algebraic topology. I'm not aware of any geometric proof of this fact. Yeah? It comes from algebraic topology.
Just a little curious.
Yeah?
Why is not 5?
Why is not 5?
Yeah. Why is not 5?
This can't. It is related to sphere bundles over spheres and topologies of these, and there is. It just doesn't. It just doesn't occur there. Yeah. See, it's a topological conclusion, really, which is not obvious at all. So what can one say about these cases? One is when the number G is different from 4, so we have 1, 2, 3 or 6, then the hypersurface must be homogeneous if we assume we have a complete hypersurface, or it must be just an open part of this. That's why I write there locally. This was proved by Cartan for G equal to 1, 2, 3, and for G equal to 6 it was proved by Dorfmeister-Neher and by Miyaoka. Again there, it is quite remarkable that this case, when we have 6 distinct principal curvatures, this can only arise on a 7-dimensional sphere and on a 13-dimensional sphere. It's again related to topology. Yeah? And in the case of a 7-dimensional sphere, it was Dorfmeister-Neher who settled the problem, and in the case of a 13-dimensional sphere, it was Reiko Miyaoka who settled this problem, I think last year. It was a long-standing problem. Yeah. Now the homogeneous hypersurfaces were classified by Xiang and Lawson in the 70s. So homogeneous hypersurfaces in spheres are known, and there's actually quite a nice description of them. So the way to do this, or to describe them, suppose we have a homogeneous space, G over K. G is a group acting on the space, and K is the stabilizer. then we get the isotropy representation of this space. This is the action of the tangents of the stabilizer at the point O. So K is the stabilizer of G at the point O. So we have a natural action of K on the tangent space of the symmetric space. Yeah. And this action here, this is called the isotropy representation of the homogeneous space. Yeah? So the group K acts on the tangent space. Now, when we assume that this here is a symmetric space, or a symmetric sphere, and we assume that this symmetric space has rank 2, then this action here becomes an isometric action on this Euclidean space with codimension 1 orbits, but it preserves lengths of vectors. So it is an action which acts on the sphere in the tangent space with codimension 1 orbits. Yeah? And so when one has a symmetric space of rank 2, so for example a Grassmannian of 2 planes in Rn, this will be a symmetric space of rank 2, this construction gives homogeneous hypersurfaces in a sphere. And what Xiang and Lawson proved is that the converse is true, that every homogeneous hypersurface in a sphere arises as an orbit of the isotropy representation of a symmetric space of rank 2. And there is a list of such spaces. It's a rather short list, and this gives the classification of the homogeneous hypersurfaces in spheres. So this is related to symmetric spaces of rank 2. This is quite remarkable. And it's actually quite mysterious why this is. I don't think anyone has a good explanation why homogeneous hypersurfaces in spheres are related to isotropy representations of symmetric spaces. Yeah? Why symmetric spaces play a role here. Now you see there is one remaining problem is when the number of distinct principal curvatures is 4. And this is quite remarkable. Namely, there exist inhomogeneous hypersurfaces with 4 distinct constant principal curvatures. And the first such examples were produced by Ozeki and Takeuchi. And a few years later, then Feroz, Karcher and Münzner, they produced a whole series of inhomogeneous hypersurfaces in spheres. And they are all related to representation theory of Clifford algebras. Yeah? Quite remarkable that suddenly Clifford algebras come into the picture here. It's quite unexpected. So this makes, of course, the classification problem much more difficult when there are 4 distinct principal curvatures. You don't get homogeneity, yeah? So there are no groups involved. That's much more difficult. But there has been some recent progress on this. For a long time nothing was known, but recently Cecil, Chi and Jensen, they proved that apart from the homogeneous ones with 4 distinct principal curvatures and these inhomogeneous ones which were constructed here, there are no other ones with few possible exceptions, and these exceptions can only arise in spheres of dimension 19 and 31. So this problem has been almost solved now. It's just open in these 2 dimensions, dimensions 19 and dimension 31. The proof is very complicated, and I think this is too difficult for me. Very long computations. Okay. So this is where we are with the sphere at the moment. And again, here is a comment. It's a nice, interesting problem, but I think it's a very difficult problem, that no other symmetric spaces are known which admit inhomogeneous hypersurfaces with constant principal curvatures. So we saw in real hyperbolic space, Cartan proved they're always homogeneous. in this sphere, we see here, there are these inhomogeneous hypersurfaces which were constructed here. But when you go to any other space in this list of symmetric spaces here, there is not a single example known of an inhomogeneous hypersurface which has constant principal curvatures. And it's not clear at all whether they exist or not. But it would be very good to prove there is. I mean, just pick any of these spaces and to prove there exists none, that would be very good. Yeah? So that's a very interesting open problem. So I want to say a bit about, go a little bit further here in my list of spaces. Talk about complex projective space and complex hyperbolic space. The situation there is more complicated. These spaces do not have constant curvature. So the curvature varies, but still we have positive or negative curvature, and there's quite a large symmetry group. It's well understood, these spaces. One can write down the curvature tensor explicitly, so a lot of information is really known. One can write down Gauss-Codazzi equations explicitly, so that's fine. Now the homogeneous hypersurfaces in complex projective space, they were classified by Takagi, and the proof for this is it's not so difficult. On a complex projective space, CPN, we have a natural S1 bundle over the complex projective space is the 2n plus 1 dimensional sphere. Yeah? What points in complex projective space are lines in an n plus 1 dimensional complex vector space, and so then any such line intersects the sphere in a circle, which gives us a circle bundle over complex projective space, and this is the famous Hopf vibration. Now when one has a homogeneous hypersurface in complex projective space, so one has a subgroup of the isometry group of complex projective space acting isometrically on CPN, one can actually lift this to an isometric group action on this sphere, which also then has a codimension 1 orbits. Yeah? So every homogeneous hypersurface sphere pulls back to a homogeneous hypersurface in the sphere, and they were classified by Xiang and Lawson, and we saw these are just the isotropy representations coming from symmetric spaces of rank 2. And the ones one gets in complex projective space are precisely the ones where the symmetric space is Hermitian symmetric, because this is exactly the condition one needs, that the group action preserves the fibers of this fibration. Yeah? So this is what Takagi observed, is that one needs precisely the Hermitian symmetric spaces of rank 2 to produce the homogeneous hypersurfaces here. Yeah? And then one can calculate their principal curvatures, and it turns out that G is either 2, 3 or 5 for any of these. Yeah? So that's a straightforward calculation. Then of course no one would like to know the converse. Yeah? So if you have a hypersurface with constant principal curvatures in complex projective space, is it any of these? That's a natural question. Well, first, G equal to 1 is impossible. I think it was first mentioned by Tashiro and Tachibana, but this is quite an elementary consequence of the Codazzi equation, that one can't have an umbilic hypersurface in a complex projective space. So the next question is, what happens when G is 2? And then Takagi proved it's actually one of these examples, and he then, with some more complicated calculations, he also proved the same holds when G is equal to 3. Yeah, so Takagi could prove that the converse holds if the number of distinct principal curvatures is at most 3. Yeah, so then we have a homogeneous hypersurface. Okay. There is another result. If one has a Hopf hypersurface with constant principal curvatures, then the hypersurface must be homogeneous. Now, Hopf hypersurface. I'll explain what this is. It's actually a number of different definitions which are all equivalent. So suppose we have a hypersurface in complex projective space, CPN. Pick a point and say a normal vector psi which is perpendicular to the hypersurface. Okay? So this is perpendicular. Now complex projective space has a complex structure, J, so when we apply the complex structure to this normal vector, we obtain a tangent vector. Yeah, so this is a normal vector and this is a tangent vector. And now the hypersurface is said to be is a Hopf hypersurface if this tangent vector is a principal curvature vector. This is one characterization of it. Another characterization of a Hopf hypersurface would be, see, when we do this at all points of the hypersurface, what we get is a one-dimensional distribution on the hypersurface given by all these tangent vectors. Yeah, it's a one-dimensional distribution on the hypersurface. This one is always integrable, so there will be curves which are then tangent to all these vectors, J of the normal vector. And if these curves are geodesics, this is equivalent to saying that the hypersurface is a Hopf hypersurface. Yeah? So I wrote this all down here in a number of conditions. So the following is equivalent. We have a Hopf hypersurface that this vector field on P, so this one here, when we do this at every point, what we get, this is known as the Rape vector field, is a principal curvature vector everywhere. Yeah, so that's quite a restrictive condition. Or the Rape vector field on P is geodesic. That's what I just mentioned, that the integral curves of this vector field are geodesics on the hypersurface. Another equivalent condition is that, of course, you see, when this vector is this vector field is principal curvature vector everywhere, then the orthogonal complement of what is spanned by this vector must be invariant under the shape operator, must be invariant under the second fundamental form. But the orthogonal complement of this is just the maximal complex subbundle of the tangent bundle. Yeah? So this is an equivalent condition. For that we have a Hopf hypersurface. See, this is actually quite a nice condition which you can impose on any Kähler manifold, complex manifold, yeah, because you just need the complex structure to do all this. But there is also another condition of this which doesn't involve the complex structure. This is the last one, that the hypersurface is curvature adapted. And this condition means the following. It's curvature adapted. So when we have a normal vector, we get the shape operator. So A psi. So this is the shape operator. The eigenvalues of this are the principal curvatures. And then we get the normal Jacobi operator. So the normal Jacobi operator, so let R be the curvature tensor of CPN. And so what we then insert is the normal vector in two of the three slots of the curvature tensor of the ambient manifold of CPN. So denote this by R psi. So this is the, what is this called? Normal Jacobi operator. Okay. That's also a symmetric tensor field on the hypersurface. And the condition that P is curvature adapted, so P curvature adapted, is equivalent to saying that these two operators commute. Yeah. Since both are symmetric endomorphisms, they commute. This means that they are simultaneously diagonalizable. Yeah, that's an effect from linear algebra. Yeah, when you have two symmetric endomorphisms, they commute precisely if you can diagonalize them simultaneously. Yeah, they have a common eigenbasis. Yeah. So this is an invariant description. So this is an invariant description of Hopf hypersurface, not using the complex structure. Yeah, just using the geometric object of the shape operator and then the geometric object coming from the curvature tensor, the Jacobi operator. Okay. So I spend a bit of time explaining this because this is quite a good condition which one can use to try to generalize this result by Kimura to other spaces. Okay. So Kimura proved is that when this condition holds, any of these condition holds, and we have constant principal curvatures, then the hypersurface must be homogeneous. Okay. Now in complex hyperbolic spaces, the homogeneous hypersurfaces are known, they are classified, but I won't say much about how this is done. It's actually quite a long list. And quite, yeah, so we don't learn much from this if I explain this. So they're all known. And one can calculate their numbers, the number of distinct principal curvatures, and the numbers arising here are 2, 3, 4, and 5. So again, it's restricted. It's not clear to me why. See, when we look at all these spaces I discussed so far, the number G is restricted to, I mean, the highest number we encountered so far was the number 6 for spheres. Yeah? But it's independent of the dimension of the manifold. And it's not clear to me why there is such a bound, really, for all these. So again, G equal to 1 is impossible. This comes from the Codazzi equation. When G is equal to 2, then the hypersurface must be homogeneous. This was proved by Montiel. And for G equal to 3, also there it is known. So I proved this with my collaborator, Carlos Diaz Ramos from Spain, that the hypersurface must be homogeneous. Yeah? So it's quite similar result. And also, it is true that when we have a Hopf hypersurface with constant principal curvatures, then the hypersurface must be homogeneous. So Kimura's result, the analogous statement for hyperbolic space, also holds. Yeah? So there's quite similarities here between projective and hyperbolic space. But there is, as a comment, again an observation here. In complex hyperbolic space, every homogeneous hypersurface is a Hopf hypersurface. Yeah, this comes out when you look at the classification by Takagi. The consequence is the hypersurface is a Hopf hypersurface. But in complex hyperbolic space, there are homogeneous hypersurfaces, and actually almost all of them, almost all of the homogeneous hypersurfaces are not Hopf hypersurfaces. Yeah, this is it's quite remarkable, and I don't really. Again, you see, sometimes say I don't know the reason why. I mean, I'm thinking about this, but I don't know why it is. It just comes out of the classification, but I don't have really a good justification for this, why this is the case. Yeah? That is something that distinguishes projective and hyperbolic spaces. Yeah? Yeah?
Your question. So sorry. My question related to isoparametric
yeah.
hypersurface defined by isoparametric
yeah.
function. And any homogeneous hypersurface in complex space form is an isoparametric hypersurface. Is it true?
Every homogeneous hypersurface
in CPN or complex hyperbolic space
is a
isoparametric hypersurface.
This is
isoparametric function.
This is yes, this is correct.
Correct.
Yes.
And also in complex hyperbolic.
it's also true.
CHN case, and you can describe concretely isoparametric function?
No.
No.
Yes.
How about the Hopf hypersurface?
I think for the Hopf hypersurfaces one can write this down using the Lorentz model, the anti-de Sitter model, but for the non-Hopf hypersurfaces it's probably very difficult.
Existence of isoparametric, corresponding isoparametric function exists.
Yes.
They're difficult to describe.
Yes.
Explicitly.
Yes.
In your comment, the first sentence, Takagi have shown that in complex projective space, every Morning hyperspace is Hopf.
No, it follows of his classification. Yes, so you look at his list and see they're all Hopf hypersurfaces. Yeah.
But in complex hyperspace, they are count example.
Yes.
The lecture follows
Yes, that's right. Okay. So here are some questions. So all known hypersurfaces with constant principal curvatures in complex projective space are hypersurfaces, are Hopf hypersurfaces. Is this true in general? I don't know. That's an interesting question. Yeah. See, one idea one could have, but that doesn't lead to anything, is using the Hopf vibration again from the sphere to complex projective space. So when one has constant principal curvatures here, try to look at the pullback in the sphere, and then what can we say about this? Now, the thing is, when this is complex, when we have constant principal curvatures here, then the pullback has constant principal curvatures here. That is true. But now when we have constant principal curvatures in the sphere, and we assume that this hypersurface is invariant under the vibration, under the circle vibration here, so we can push it down to complex projective space. So does this also have constant principal curvatures then? And the general answer is no. Yeah? Because when you start with constant principal curvatures here and assume it is invariant under the vibration, then one does not get in general constant principal curvatures here. Yeah. This is actually the first example was produced by Qiming Wang some time ago for this. And in both spaces, you see all known hypersurfaces with constant principal curvatures in complex projective space and complex hyperbolic space are locally homogeneous. Is this true in general? So it's again my question of trying to find, are there any inhomogeneous hypersurfaces? Yeah, that's an open problem. An interesting open problem. So I want to say something about, just to give you an idea how, like of one result in this area and how to prove it, to give you the feeling of what is involved. So this is the classification which I did with my collaborator Carlos Diaz-Ramos, about the classification of hypersurfaces with three distinct principal curvatures in complex hyperbolic space. And any such hypersurface is one of these. So I want to describe what they are. The first one is a ruled real hypersurface generated by a Horner cycle in a real hyperbolic plane in complex hyperbolic space. So what we take is an RH2 inside of CHN, complex hyperbolic n space. Now real hyperbolic space, you think about, there are many models for real hyperbolic plane. Think about the Poincaré model of this. So this is the unit disk with a particular metric. This gives a real hyperbolic plane. And inside there we pick a horocycle. So I explained what the horocycle is, and when we take the Poincaré model of real hyperbolic plane, a horocycle is, it's a round circle, really a round circle, which is tangent to the boundary of the real hyperbolic plane. Yeah, so this here is a horocycle. This is a round circle. So this horocycle lives in RH2, and so in complex hyperbolic space. Now at each point of this horocycle, we now attach perpendicular to this, complex perpendicular, we attach a complex hyperbolic hyperplane. Okay? So this we do at every point. So what we get is, it's not obvious from this picture, but we get actually a well-defined smooth hypersurface in complex hyperbolic space. Yeah, and you see, I explicitly, it's a ruled hypersurface. It's ruled by these complex hyperbolic hyperplanes. Yeah, at each, it's like, so we have a curve, and then we attach many hyperplanes. Yeah, but this gives a well-defined hypersurface, and this is actually, it's a homogeneous hypersurface. And this is homogeneous, but then also the equidistant hypersurfaces are homogeneous. In the second part, we have a tube around the complex hyperbolic, k-dimensional complex hyperbolic space in CHN. Now this is not so difficult. We can also take a real hyperbolic space of half dimension and complex hyperbolic space, take the tube around them, and they are homogeneous, but generically these have 4 distinct principal curvatures, and it just happens that generically they have 3 distinct principal curvatures, but for this particular radius, when r is equal to the logarithm of 2 plus square root of 3, we actually, 2 of the 3 principal curvatures just happen to coincide, so we get only 2. Yeah. So we get this family of tubes with 3 distinct principal curvatures, but for a particular radius we have only 2. Just happens so. And then we get a certain tube of a particular radius around a particular submanifold in complex hyperbolic space. And this is the first example. I want to explain what this is, which shows that it is more complicated with the homogeneous hypersurfaces in the hyperbolic case than in the projective case. So I want to explain how this FK is constructed. So the complex hyperbolic space it's a homogeneous space G over K, and G is the isometry group, or the identity component of the isometry group, which is the special unitary group of the complex Cn plus 1 with the standard metric of signature 1. And this is the stabilizer at a point. This is SU1n is a non-compact, simple, real Lie group, and for such type of Lie groups there is a beautiful structure theory, and part of the structure theory is due to Iwasawa, which says that any such group, semi-simple non-compact real Lie group, has an Iwasawa decomposition, so it's diffeomorphic to the product of the stabilizer of G, an abelian subgroup, which is one-dimensional in this situation, and the nilpotent subgroup. Yeah? And since, see, when we factor out k, G over k, what is left is A times n. So what we see is that A times n acts on complex hyperbolic space, and it acts freely and simply transitively. Yeah, because all the points, all the isometries fixing a point are in k, so none of them can fix a point. Yeah? So this gives this Iwasawa decomposition gives a model for complex hyperbolic space. So we can realize this as a solvable Lie group equipped with a suitable left invariant Riemannian matrix. Yeah, and so suddenly we are in the realm of Lie groups with left invariant metrics and can use the theory for Lie groups with left invariant metrics, which is somehow simpler. Yeah? Now, from the group, of course, what one does is one linearizes. So from the group, we linearize, we go to the algebra. Yeah, so on Lie algebra level, we get then this Iwasawa decomposition here that just corresponds to this. Here we get the unitary algebra plus A, one-dimensional abelian algebra, and N. And this N happens to be a Heisenberg algebra. Yeah, it has a one-dimensional center, and the orthogonal complement is a complex vector space of the corresponding dimension. Yeah. So in fact, maybe it's useful to mention here, when we take this nilpotent group N, this nilpotent group N acts on CHN with codimension 1 orbits. Yeah, because this is one-dimensional, and the orbits are horospheres. Yeah, so this is a simple way to construct horospheres on complex hyperbolic space. Take the orbits of this nilpotent group N in an Iwasawa decomposition. So now what we take is, we take a k-dimensional real subspace of V. So this is a complex subspace, Cn-1, and in there we pick an arbitrary real subspace. And then take the orthogonal complement of that real subspace in the complex vector space. Yeah? So then we add everything together. We take A plus this bit plus the center part. And then the way this is a solvable algebra. We know the algebra structure, and it's easy to verify that this is a subalgebra as well. Now, since this is a subalgebra, we can exponentiate, and we get a corresponding group, subgroup, and we look at the orbit of this subgroup through the origin, and what we get is a submanifold in complex hyperbolic space. Yeah? So this is a submanifold. It's homogeneous and ruled with a real normal bundle of rank k. So which means the normal space has dimension k. It's a real subspace and it has dimension k. And the tubes around this submanifold are homogeneous hypersurfaces. Generically, they have 4 distinct principal curvatures, but it happens that for a particular radius there are 3, and this is what arises in the classification. Yeah? So you see that in some way it becomes more complicated now when you write down the homogeneous hypersurfaces. Okay. And I just want to, at the end, to finish off, give you an idea of how a proof for such a result looks like. So we have 3 distinct principal curvatures. It's our assumption. Each of these has certain multiplicities. And what we then also get is a decomposition of the tangent bundle of the hypersurface into 3 eigenbundles. Yeah? That's what we can get from our assumption. We have our local unit normal field. We apply J to it. We get this Hopf vector field or Reb vector field. And we can assume that P is not Hopf, so that J psi is not tangent to any of these 3 subbundles, because if it is Hopf, then we can apply the classification. We know it's homogeneous. Yeah? So we can assume it's non-Hopf. So the first step is to show, see this vector field, J psi, then since it is not contained in any of them, there are at least 2 non-trivial projections. Yeah, there could be 3 non-trivial projections onto these subbundles, but there are at least 2. And the first step is to prove that there are at most 2 non-trivial projections, which means that the Hopf vector field J psi can be written as a linear combination of 2 vectors in of two principal curvature vectors. Of two, but not three. Yeah? And that's quite an important piece of information that one gets from the Gauss-Kodazzi equations. Yeah? So this is the first step. The second step is one can show that, so if we assume that j psi lies in here, one can show that there exists a vector A in the third eigenspace, so that when we take all these vectors together, A, u1 and u2, and we add the normal vector, we get a complex subspace of the tangent space. Yeah? So this tells us something about how these vectors are related with each other. So they can't be arbitrary. They must span a complex. They form a complex subspace. So this must hold on an open neighborhood of P. So this gives us vector fields. Once we have vector fields, we can differentiate. That's why I'm going to do this. And one can show that the integral curves of this vector field A are geodesics in the hypersurface, and all three vector fields span an autoparallel distribution. So they produce three-dimensional totally geodesic submanifolds on the hypersurface. The next step is inserting all this information into the Gauss-Kodazzi equations. So when we assume that the multiplicity of a principal curvature is bigger than 1, one gets a simple equation. Yeah? The 4 times the product of lambda 3 with lambda I is equal to 1. Yeah? But this must hold for lambda 1 and for lambda 2. But since lambda 1 and lambda 2 are distinct, we must know that, we conclude that one of them must have multiplicity 1. Yeah? So we can assume that, say, the second multiplicity is 1. Yeah? That's a restriction we get. Then continue the calculations. So if the first multiplicity is bigger than 1, one gets some information. It's this, you see, it's not important really to see what these values are. What you should get from this is one can calculate explicit values for the principal curvatures, and one gets somehow some information about the structure of the eigenspaces. Yeah? And the same happens when the multiplicity is 1. Although one can't explicitly write down what lambda 3 is like, there is just a bound for this. Yeah? And then one can write down. So if one does some manipulations with Gauss-Kodazzi equations, one gets some information about the values of the principal curvatures. And then the strategy is what Cartan did. One looks at equidistant hypersurfaces. So one goes in normal direction and looks at hypersurfaces. What happens to the structure of the hypersurfaces when one goes in normal direction? Yeah? And one gets focal sets again. And one can investigate the structure of these focal sets using Jacobi field theory. And if one works out everything nicely, so what one gets is one gets a 2n minus m1 dimensional focal manifold if the multiplicity is bigger than 1, or a hypersurface if the multiplicity is equal to 1 of our given hypersurface P, which has a totally real normal bundle. So the normal space at each point is real, and there is a unit vector field Z tangent to the maximal holomorphic subbundle of the focal set, such that the second fundamental form has this explicit description. Yeah? So using the theory of Jacobi fields, one can work out the geometry of the focal set. Yeah? So the focal set one knows explicitly the second fundamental form of the focal set. But you see, this is now more complicated than in the real hyperbolic case. In the real hyperbolic case, we just got 0 for the focal set, 0 for the second fundamental form, so it must be totally geodesic. Here, we get a non-zero second fundamental form. So what one needs to know is to classify all submanifolds which have this particular second fundamental form. Yeah? But I know one example. This is the one, this Fk, which I explained before, has exactly this second fundamental form. So the final step is to prove a rigidity result, which says that if one has a submanifold which has exactly these properties, it's just a copy and paste here. But yeah, so if you have submanifold with exactly these properties, it must be congruent to this submanifold. Yeah? And this finishes the classification. So this somehow gives you an idea of how to prove such a result. And I think I stop here for today. Thank you for your attention.